Hello. Today I'll be going over AICE Physics Syllabus Code 9702, Paper 23 from October-November 2017. Still studying waves, this is question number 4 from that paper. It reads, by reference to the direction of propagation of energy, explain what is meant by a longitudinal wave. Remember that a longitudinal wave is one where the particles of the medium oscillate parallel to the direction of propagation of energy. So we'll put that into words. The particles of the medium oscillate parallel to the direction of propagation of energy. Part B, a car horn emits a sound wave of frequency 800 Hz. A microphone and a cathode ray oscilloscope, CRO, are used to analyze the sound wave. The waveform displayed on the CRO screen is shown in figure 4.1. Determine the time base setting in seconds per centimeter of the CRO. Because they give us the frequency is 800 Hz, the first thing that we can do is calculate the time period. So remember that frequency is equal to 1 over t, and t is equal to 1 over the frequency. So those quantities are inversely related. So because we want to know the time period, we're solving for the time base setting. We can substitute in 1 over 800 Hertz. One divided by 800 Hertz equals 0.00125 seconds. Now looking at the data in figure 4.1, we see that a centimeter is one of these squares right here. The crest of the wave starts here, and 2.5 centimeters from there we see the exactly identical point, the next crest. So the wavelength sort of on the screen is 2.5 centimeters, but remember we're trying to figure out what is the setting on our oscilloscope, and so the physical distance here is really representing a time, and we know how much time one wave occupies, because if frequency is the number of waves per second, then period is the number of seconds per wave. So it's helpful to sort of write out what we've got. 0.00125 seconds per wave. That's the definition of time period, the number of seconds per wave. And now we've just deduced from our cathode ray oscilloscope that one wave occupies 2.5 centimeters. So we were really trying to get to the idea of how many seconds per centimeter, and so if there are 0.00125 seconds per one wave and one wave per 2.5 centimeters, then by multiplying these two factors, we're canceling out the word wave or division, and we're in seconds per centimeter. And so our calculation becomes 0.00125 divided by 2.5. Remember, we just multiply everything in the numerator and divide by everything in the denominator. And so we get 0.0005, or 5 by 10 to the negative 4 seconds per centimeter. The question goes on to read, the intensity I of the sound at a distance r from the car horn in B is given by the expression I equals k over r squared, where k is a constant. Figure 4.2 shows the car in B on a road. Have you committed that figure to memory? Good. An observer stands at point O. Initially, the car is parked at point X, which is 120 meters away from point O. The car then moves directly towards the observer and stops at point Y, a distance of 30 meters away from O. The car horn continuously emits sound when the car is moving between points X and Y. So Here we can see 90 meters, about the length of a football field. This person is continuously blaring their car horn as they speed or as they move towards this observer. Doppler effect questions. It reads, the sound wave at point O has amplitude A sub x when the car is at x, and amplitude A sub y when the car is at y. Calculate the ratio, the amplitude y to the amplitude x. So we're looking at how much, amplitude is related to intensity, and we're sort of related to the energy or the power per area, right? It's what intensity is, and so kind of be thought like not exactly how much louder it is, y compared to x, but that's sort of the idea that we're getting to. Like this, the observer here will hear the car horn louder here than they did here, and how did the amplitude of the wave, which is related to the intensity, and the human perception of intensity is loudness. So we're really interested in the amplitude of the wave itself, which remember is the maximum displacement. If we look at our oscilloscope, we could think of the amplitude as sort of the distance from equilibrium up or the distance from equilibrium down, the maximum displacement or the minimum displacement, if you think about this as like a negative value. So it's not the entire height of the wave from crest to trough, but sort of half of that distance, right? So from the undisturbed equilibrium position up is the amplitude. And so we're looking at the ratio of the amplitudes. The ideas that we have to work with are that the intensity is equal to the constant k over r squared, and we should recall from our reading that intensity is proportional to the amplitude squared. And so these two ideas together will allow us to get to the ratio ay over ax. If intensity is proportional to amplitude squared and intensity is equal to k over r squared, we could think about this as that the intensity is proportional to 1 over r squared. K is just some constant. We could set it equal to 1 with sort of arbitrary constants, arbitrary units, and then they would cancel out. If I is proportional to a squared and I is proportional to 1 over r squared, then a squared is proportional to 1 over r squared. And we could just take the square root of all of that and realize that the amplitude is proportional to 1 over r. This might be the most sort of elegant path to the solution, to think about it like this. So now we're just sort of looking at the amplitude is inversely proportional to the distance there, and so we can set it up the way that they ask us to solve the amplitude at y compared to the amplitude at x. A sub y over a sub x would be equal to, so we sort of think about like if we're interested in y, well then that's going to be the value corresponding with y in the denominator over here, right? It's inversely related to that. So that distance was 30 meters. Likewise, a sub x is going to be inversely related to the distance at x, which was 120 meters. And so 120 meters divided by 30 meters is a ratio of 4. Another way to sort of think about this calculation is to substitute in amplitude squared here and just sort of plug in k over r squared into the ratio here, and then you eventually take a square root at the end there. But 4 is the correct answer. It's possible to arrive at this correct answer by sort of other paths than the one that I've shown here. It goes on to read, when the car is parked at x, the frequency of the sound from the horn that is detected by the observer is 800 Hz. As the car moves from x to y, the maximum change in the detected frequency is 16 Hz. The speed of sound in air is 330 meters per second. Determine to two significant figures the minimum wavelength of the sound detected by the observer. Minimum wavelength will be maximum frequency. And if the total change is 16 Hz, then the maximum frequency observed is going to be 816 Hz. So the car horn to the person driving the car will sound at 800 Hz, but the observer, as that car speeds towards the observer, will observe a frequency of 816 Hz. The velocity of the sound wave is 330 meters per second, and the velocity of a wave is equal to the wavelength the thing we want to know, times the frequency. So we can solve for the wavelength as the velocity divided by the frequency, 330 meters per second divided by 816 hertz. Hertz is the same thing as a reciprocal second, like you see here in the numerator, and so those units are going to cancel, and we'll be left with meters of wavelength. And so we've got 330 divided by 816, which yields 0.40 meters. The final question asks the maximum speed of the car. And so here's where we run into the Doppler effect equation. Because the car is speeding towards the observer, that's the situation where we would subtract in the denominator rather than adding. (816 hertz is the observed frequency. 800 hertz is the frequency of the source. The speed of sound is 330 meters per second divided by 330 meters per second minus the velocity of the source. Multiplying both sides of the equation by this term here, we get 816 hertz times 330 meters per second minus the velocity of the source equals 800 hertz times 330 meters per second. Dividing each side of the equation by 816 hertz. We get 330 meters per second minus the velocity of the source equal to, so here we've got 800 times 330 divided by 816. And then subtracting 330 from both sides, then we'd divide each side by -1, and we'd realize that the velocity of the source is about 6.47, and we could round our answer to 6.5 meters per second.